end up making the decision. Okay. So what are we doing here? So to calculate our p-value, what do we need? First of all, we need to sign in the alternative hypothesis. Way back when, we decided we were going to test not equal to. Next thing we need is our test statistic. We found a while ago that the test statistic for this problem was 1.7854. This rule right here, get it where you can see it. This rule right here tells me what? This tells me to find my p-value for this. I need to find the area to the right of 1.7854. And I need to find the area to the left of negative 1.7854. Well, can we do that? Absolutely, we can do it. All we got to do, because of symmetry, is find one of them. And then multiply it by 2, because this area over here, again, because of symmetry, is going to be the same value. So we got kind of mu equal 3 residing there in the center. Okay, so let's do the t-distribution. So guys, down here we got something called a t-CDF, which is the equivalent of the normal CDF. We use normal CDF, we're using a z-distribution. t-CDF if we're using the t-distribution. So I want the 1.7854 up to infinity. And these things are a function of degrees of freedom, not 0 and 1, so I have to use degrees of freedom. So what I'm doing here is I'm finding this area right here. Didn't have to. I could have found the other. I just didn't want to put in a bunch of negatives. I could have said, well, I want to find this one over here. Well, that's okay. I'd go negative E99 up to negative 1.7, what was it? 854 degrees of freedom. And I get the same thing. Well, I don't get the same thing because I typed it in wrong. It should be insert a 7 right there. And now I get the same thing. Okay? So it doesn't matter. But because I need both areas, I have to multiply that by 2. And I get my p-value equals 0.0803. That's the hard part. Everything else is fine and dandy. All right? So, step 4. It's decision time. Guys, your decision. The criterion for the decision is you compare your p-value to alpha. If your p-value is less than alpha, then you do what's called reject H sub O. If your p-value is greater than or equal to alpha, then you fail to reject H sub O. Our p-value was 0.0803. Our p-value back from step number 2 was 0.05. Our alpha. Our alpha was 0.05. Our p-value we calculated to be 0.0803. This is greater than 0.05. 0.0803 is bigger, so we fall in this category here. Our final decision is fail to reject H sub O. Back to our initial set of hypotheses, mu equal 3, testing against mu not equal to 3, we must fail to reject this claim. So at the end of the day, we cannot reject the claim that the mean wait time is equal to 3. So we're going to dispose of the alternative in lieu of the null. If we had rejected the null, then we would draw a line through the null hypothesis, and our focus would be on the truth, so to speak, the knowledge base, the improvement of knowledge, if you will, on what we have determined in the alternative hypothesis. I would conclude, therefore, that the mean is not equal to 3. It's either higher or lower, and based on 3.2, we would say it's higher. The final step is to create your 95% confidence interval. Now, you don't always create a 95% confidence interval. In fact, your confidence interval depends on the alpha that you select way back in step 2. Back in step 2, I told you that we had one of 4 choices, actually one of a lot of choices, but these are the 4 choices that you see most in literature. These things correspond to, this decision for alpha corresponds to the confidence level that you present. If you present a if you tested alpha 0.05, the corresponding confidence interval will be 95%. If you tested 0.10, the corresponding confidence interval will be 90%. Probably see what's happening, right? Change this to a percentage. Subtract it from 100. 99%. 99.9%. Sometimes you get into wacky alpha levels. It just means you use a wacky confidence interval level. Okay? These are the typical choices in research. In fact, without question, you don't see anyone that deviates much from the 0.05 unless you get into situations where you get some alpha levels that are inflated just because of the dynamics of the test. But we don't study that in this level class. So 95% confidence interval, I'm going to leave for an exercise. No, I'm not. I'm going to go ahead and make it happen. So guys, remember x bar plus or minus, we need our t critical. Sx over square root of n. We know that this is 3.2. Our t critical, we'll come back and get that in just a second. 0.8 over the square root of 51. Guys, how do we get our t critical? Just like we did before. Start out with 100%. Subtract the 95% or whatever we want to calculate the interval of. Divide by 2. Find the area to the left of 0.025. So guys, we can use our inverse t for that. 0.025, comma the degrees of freedom. So our t critical for the 95% confidence interval would be negative 2.009. Okay, so that'd be the negative. The plus would be on the other side of the distribution. So guys, we can put that in very, very quickly. So 3.2 minus 2.009 times 0.8 divided by the square root of 51. I'm going to do that again for the plus. Guys, I get the 95% confidence interval as 2.97 to 3.43. Now, your head's probably spinning, thinking, what in the world is Darbro talking about? This is crazy. It is insane. Absolutely insane. What we just did, we just conducted a t-test for the claim that the wait time at Tim Hortons is 3 minutes from 8 a.m. to 10 a.m. using a sample of n equal 51 customers who waited on average 3.2 minutes with a 0.8 standard deviation. We wanted to test not equal. For some reason, that was just our motivation. We used an alpha 0.05, that's fine. We calculated our t critical value to be one point, then we'll screw this up because I just did 1.7845, I do believe. Shoot. Yeah. We calculated our p-value. To be 0.083. Our fourth thing is our decision. We failed to reject H sub O because our p-value was greater than our alpha. Our 95% confidence interval turned out to be 2.97 to 3.43. All right, guys, so in a nutshell, this is what we just found right here. There's inconclusive evidence to reject the claim that the mean wait time is 3 minutes based on this sample. Now, you're sitting there looking at all this stuff, and you're like, man, I don't understand. There's no way in the world I can ever get a t-value, a test critical, a p-value. I have no idea what you did about doubling all that area under the curve. That stuff's crazy. It's insane. Well, guys, your calculator does it for you. Lucky you. Okay? Let's go to stat. Let's go over to test. And because of the dynamics of our test, as I've described earlier in this video, we would conduct a t-test. I have statistical results, not my 51 measurements. So mu 0 is the value that goes in the null hypothesis. That's going to be a 3. Our sample mean was a 3.2. Our sample standard deviation was a 0.8. And our sample size was a 51. The inequality that we used was the not equal to. I told you earlier there's only 3 choices: not equal to, less than, greater than. Choose the one that corresponds to what you're testing. Come down and hit calculate. And you see some numbers that look eerily familiar, right? There's the 1.7845. We're off a little bit because when I calculated, why are we off a little bit? We shouldn't be off. Did I make an error? Let me see. So I had 3.2 minus 3 divided by 0.8 divided by the square root of 51. Wow, I must have, yeah, I did. I had to do a, well, all right. You guys probably, when I was doing the video, probably saw what I was doing wrong. I missed something there, so that should be 7854. And that may have been what I actually, it is what I wrote down. I just wrote it down. I wrote it down wrong there. So, but anyway, you can, let me just run the t-test again real quick. Anyway, you can come on down. You see your p-value is 0.0803, which is exactly what we got here. Use the same decision rule. Our p-value is greater than or equal. Ooh, yeah, greater than or equal to our 0.05. And 95% confidence interval. This is kind of cool. Stat test. We did a t-test. So you should know by now we conduct a t-interval. I think this is kind of cool. Everything's there, right? Your calculator, it knew you were coming. Because when you do a t-test, it is customary to do a t-interval. So it is waiting on you. Make sure your confidence level corresponds to the alpha that you chose. And guys, when you get that, you're going to see that your confidence interval corresponds to 2.97, 3.43 to what we had before. All right. So, boys and girls, you got a problem. Let me try to come up with something here. So the mean exam score for all Math 1500 students taking the class traditionally that's in the class has been mu equal 80. So I've taught this class over 100 times. I've kept really good records. Dr. Defcoda, Ms. Wall, so on and so forth. We all kept good records. And we have found that the mean exam score for students taking this class traditionally has been 80. Is the mean exam score higher for students taking the class online? Well, I have a sample from this semester that I'm making up. I have 24 students who show up to take the final exam. Their mean score is 83 with a standard deviation of 19. Test the claim. That the mean exam score for online courses is higher than for traditional courses. Now, this is going to be one of the things that the administration is going to want to know about teaching Math 1500 online. Is there any difference in success rates? And I don't think there is really. My success rates are usually lower in the summer because of the pace of the class, and just people just got a lot of cool stuff to do in the summer, with vacations and going to the lake and doing boating and just hanging out and doing cool stuff. So success rates are always a little bit lower. So I can compare summer for summer, but ultimately what I want to do is I want to compare this overall. So how would I do something like this? Well, you're going to do it just exactly like I would tell you. First thing you would do is set up your null and alternative hypothesis. Go to your alternative hypothesis first. Is the means exam score higher? Go back to your alternative hypothesis. And use the opposite with the equal in the null hypothesis. Second thing, set your alpha. I'm going to mix it up a little bit here. I'm going to use an alpha that's goofy. Alpha equal 0.03. Third thing, use your sample data. To test H sub O. You're going to do this twofold. You're going to calculate T critical. You're going to calculate your p-value. Now guys, do you want to do all this by hand or you want to use the calculator? I would use the calculator. I would use all that geeky stuff, calculating the test statistic by hand, calculating the p-value by hand. I would leave that to the geeky people like me. I would use the calculator. I'm conducting a t-test. That's my job, to tell you which test to use, because that's theory, underlying theory, probability distributions, sampling distributions, stuff like that. Let me teach you that. When you're testing a mean where the population standard deviation is not given, you're going to use a t-test. I got two choices. I don't have my data. I don't have my 24 exam scores. I just have the final results. So I'm testing 80. The exam score was 83 for the 24 students. Standard deviation 19. 24 students showed up to take the final exam. But I am testing greater than. Come down, hit calculate. I get my values. My test statistic is 0.7735. My p-value is 0.2235. Four, decision. How does our p-value compare to our alpha? Our p-value is 0.2235. My alpha, 0.03. That's bigger. Fail to reject. There is no reason to believe that the mean is higher. Fail to reject means we accept, so to speak, the statement in the null hypothesis. So what I say here is there's no reason to reject that the mean is also 80 on the final exam score for students who are taking the exam online. I'd like to know the 95% confidence interval, but I'm not going to do that here. My alpha is 0.03. So I'm going to calculate my 97% confidence interval. Now some people will say, hey, you're doing a one-tailed test, yada, yada, yada. And I'm going to show that in just a second. But confidence level 93. Nope. 97. So the 97% confidence interval will be 74.03. Up to 91.97. All right. So that value clearly contains our 80. So we would say with confidence that there's a 0.97 probability that the mean exam score for all Math 1500 students taking the course online is somewhere between 74 and 92. Okay. Now, if you want to see how the p-value is calculated and the test statistic is calculated, guys, the test statistic is going to be really easy. It's just going to be 83 minus 80 over, what was the standard deviation, 19 over the square root of 24. Put that in our calculator. And we get 0.7735. Is that what we got before? .7735. It better be. 0.7735, yeah. I mean, I know it's going to work, but I have a tendency to do goofy stuff. Now, the p-value we got was 0.02235. .2235, right? Yeah. Now, how did we get this? Well, when the alternative hypothesis is greater than, yeah, scored higher, we're going to calculate our p-value by finding the area to the right of our test statistic. And guys, we're going to use our calculator to make that calculation. TCDF 0.7735. It's nice when it's right above that, up to infinity. With the degrees of freedom, remember sample size is 24, so we use 23. We don't multiply by 2 because we're not doing a two-tail test. We're doing a one-tail test. Okay, just as I said before. So our p-value we can see is 0.2235. All right, guys, going to wrap this up now. Just threw something at you. One tail, two tail. What's up with the whole one tail versus two tail test? What's up with all that? It's really just, well, it's going to be something I'm going to teach more in the next video. But just for understanding one tail, two tail, let's keep it simple at first. It all goes back to your alternative hypothesis. If you do a test greater than, higher than, more than for your alternative, you are conducting a one-tail test because the calculation of your p-value is confined to one tail. If you have h sub a less than, the mean is less than, the mean is lower than, the mean is not as high as, all those indicators that you're looking at less than. You are also doing a one-tail test because the calculation of your p-value is confined to the left tail. Now, sometimes we call this one-tail test when the calculation of the p-value is in the upper tail. We call this sometimes a right tail test. And we sometimes refer to this, for obvious reasons, as a left tail test. Obvious reasons. We're looking at the tail down here because we're using less than. We're looking at the tail to the right because we're looking at greater than, which is up here. Less than is to the left, okay? Left tail. In an alternative hypothesis where we test not equal to, the calculation of your p-value is in both tails. That tail and that tail. We multiply, we find one of these and we multiply it by 2 because we have to account for the area in the other tail because we're not doing a directional test. The dogs are going insane, as they usually do. But anyway, this is called a two-tail test. So it's one of those things you remember, guys. Less than, greater than, one-tail test, not equal to, is called a two-tail test. Sometimes we refer to these two as a directional test, and this is a non-directional test. Guys, that's all I got. I think I bombarded your brain enough in this one. This is a hard video. Keep in mind that the underlying theory is kind of complicated to learn at first, but conducting one of these things, which is really all you're going to need to do, is really easy. If you just pick up your calculator, find your test statistic, find your p-value, make your decision, calculate your 90, whatever, 80, 90, whatever confidence level that you're using based on your alpha, and finish up the problem. Okay? Guys, take care.